Again, everybody. So today we're going to talk about how to model epidemiological dynamics using this very general class of models known as SIR type models. So this is quite a detour from everything that's gone before in this class. Today we're not even going to really talk about any pathogen sequences or even phylogenies in this lecture. We're really going to focus in on how we can capture the epidemiological dynamics of different types of infectious diseases using simple models. But just to give you a roadmap as to what's coming down the road, this week we'll talk about epidemiological modeling, as I just said. But most of these models are quite simple, sort of ignore most of the heterogeneity or stochasticity that we would have to deal with when we work with real data. So next week, we'll go beyond the simple deterministic models that we'll consider today and consider stochastic models, and especially how we can simulate data under those stochastic models so we can actually then test our models and methods using simulated data sets, which is a very important part of this whole process, because unless we can create synthetic or simulated data sets to test our methods, there's really no way of ever knowing if our methods are actually working. Then in 2 weeks, I think that's the very first week of April, we'll try and put everything back together again by using phylogenetic models to try and reconcile these epidemiological models we've been talking about in the next 2 weeks with phylogenetic methods, and we'll specifically talk about how we can sort of develop or formulate an appropriate phylodynamic model for a given epidemiological model and then fit that epidemic model to a particular phylogeny. So that's what we're building up to, but we have some sort of ground to cover before we reach the culmination of actually being able to fit a given phylodynamic model to a given phylogeny. So this week, we're going to focus in on infectious disease modeling. And so the general goal for this week, and indeed the general goal for infectious disease modeling overall, is generally to get a better understanding of the dynamics of a given infectious disease. Arguably, there's sort of the alternative goal of being able to forecast or predict the future epidemic dynamics of a given pathogen. But this is sort of an additional goal that I would argue sort of has to be built upon the proper understanding of the epidemics of a disease in the past or its current epidemic dynamics. So the types of questions that we're going to hope to be able to address with our models today is, why do some epidemics rapidly grow when others don't? And why do epidemics ultimately decline? Why do some outbreaks take off and others do not? I think this is a question on a lot of people's minds, especially recently with COVID-19. We'd like to be able to know why this particular SARS-like coronavirus was able to enter the human population and take off, whereas earlier coronaviruses, entered the human population but did not cause a global pandemic. We're also maybe interested in the longer term population dynamics of these infectious diseases in terms of why do some diseases become endemic? And when I say endemic here, what I mean are pathogens that are able to persist in a host population over a long period of time, at least at some low level of prevalence, versus pathogens that can only reemerge in a given host population periodically through an epidemic or outbreak. And finally, we'll talk about why pathogens go extinct and how we can sort of bring about the more rapid extinction of pathogens through control measures like vaccinations. These are all the types of questions we hope to address with our epidemic models. And these are really all questions about infectious disease dynamics, changes in the population dynamics of given pathogens through space and time. So we need to have a way of modeling the dynamics of these systems. So how do we do that? Well, generally, as is the case in really much of science, we model infectious disease dynamics using dynamical systems. That is, systems that are allowed to evolve over time and space. Now, this could be something as simple as sort of modeling the trajectory of a falling apple under the force of gravity, such as Newton did in the 17th century. Or this could be something as complex as modeling the global spread of a pathogen through, say, the global transportation network. In either case, we start with a particular dynamical system, and we want that dynamical system to capture sort of the mechanisms and processes that are important to driving change in that system. And so we pick out particular state variables, or variables that we can explain the change of that system in terms of. So for a falling apple, this could be the height of that apple. For an epidemic, this could be the prevalence or number of infected individuals in the population at a given time. And then we'll describe the changes in those important state variables mathematically using what are known as differential equations. So differential equations are based on differentials, also known as derivatives. But I know that many of you probably have not thought or done much differential calculus, probably since you were an undergraduate or maybe even in high school. So our goal today isn't going to be to get into a super formal mathematical description of these differential equation type models. Our goal for today is to be able to understand what differential equations are trying to tell us in terms of how a dynamical system is able to change over time with almost no calculus involved at all. Although in the end, what differential equations are concerned with, of course, are rates of change in a given system over time, which are also known as derivatives. So everything turns out to be just a bunch of calculus in the end. But we'll mainly think about these differential equations quite simply as just a way of describing the rates at which a system changes through time. And so to try and convince you that you really don't need to understand much calculus to be able to understand differential equations, we'll start very, very simple with sort of a toy model that considers the rate at which water enters or leaves a bathtub. So what we're imagining here is that water enters the tub through a pipe and then leaves the tub through a drain. And what we want to keep track of is the change in the overall amount of water in the tub through time. So we'll let the variable WT denote the amount of water in the tub at a given time. And basically, two things are going on in this model. Water can flow into the tub, and the rate at which water flows in, or the amount of water that flows in over a given amount of time, will equal the inflow rate times the amount of time that has elapsed, which we'll call delta T. And then water can flow out of the tub through the drain. And so the amount of water that leaves the tub over a given amount of time, delta T, will be equal to the outflow rate times delta T. So using this mathematical notation, then we can track how much water enters or leaves the tub through time. So if we start with a given amount of water in the tub at time t, WT, we can calculate the amount of water in the tub after a certain amount of time has elapsed, delta T. And the amount of water in the tub after time delta T will just be equal to the amount of water that we start with, WT, plus the amount of water that flows in the tub over time delta T, which will be the inflow rate times delta T, minus the amount of water that leaves the tub over time delta T, which again will just be the outflow rate times delta T. And so to simplify our notation here, what we can do is we can capture the rates at which water flows into the tub and out of the tub just using the variables or parameters I and O. So basically I'm just rewriting the equation on top here in a simpler form here where we're capturing the rates of the inflow and the outflow with just these I and O parameters. So this is a fairly simple type of equation. This is just a difference equation that shows us how much how much water has sort of changed in the tub over time. But now we can begin to think about the rates of change as well. So in order to compute how much, how quickly the rate is changing in the tub, or how quickly, sorry, how the rate of change in the water in the tub is changing over time, we can think about how much water is in the tub at two different points in time. So time t plus delta t and time t. So if we take the difference in the water, the amount of water in the tub at these two times, we can calculate the overall change in the amount of water between these two time points, which we can just simply do a little bit of very simple algebra, and we see that the overall amount of water that's changed will be equal to I times delta t minus O times delta t. And now what we can do is we can consider the overall instantaneous rate of change. So what is the rate at which the amount of water is changing in our tub over time? And we can do this by taking the difference in the amount of water between two different time points and just dividing by the time that is elapsed, or delta t. So if we divide both sides of this equation here by delta t, what's left over is just the instantaneous rate of change, which is just equal to I minus 0. And so we can rewrite this in terms of a derivative, the derivative for the amount of water with respect to time, which will be WD over dt. And then this is just equal to the inflow rate minus the outflow rate. So what we're left with here is, in fact, a very simple differential equation describing the rate at which water enters and leaves the tub. And so we can do a quick sort of sanity check to make sure that this actually makes sense. And so we can see that if the inflow rate is equal to the outflow rate, if I equals 0, I and 0 will cancel each other out, and there will be no change in the amount of water in the tub over a particular period of time, which makes sense. If the inflow rate cancels out the outflow rate, there'll be no change in the overall amount of water. Similarly, if the inflow rate is higher than O, the outflow rate, the amount of water in the tub will increase over time. And really, differential equations can be as simple as that. Really, what differential equations are all about is tracking the change of some variable, say the amount of water in a tub, over time in terms of the change per unit of time, or the derivative of that variable. And often this is as simple as accounting for the rate at which stuff enters a particular state minus the rate that stuff leaves. So in our simple toy example of the tub, the overall rate of change in the amount of water in the tub was equal to the inflow rate minus the outflow rate. And as we'll see, even for more complex systems, this often holds true, that the differential equation for a particular variable that we're interested in tracking through time is just equal to the rate at which stuff flows in minus the rate at which stuff flows out. One final sort of complexity that we have to consider with these differential equations is that oftentimes we're not just interested in tracking a single variable through time, but we're interested in tracking multiple different variables through time, and these can be coupled together in terms of what are often called compartmental models, which track how the rate at which stuff flows between these different compartments. So these compartments can represent different tubs or different populations. And what we're trying to do in these compartments, or in these compartmental models, is track how the change in one particular compartment, in our case, a particular tub, is coupled to the change in another compartment. So in our simple bathtub model, we can think about the rate of change in a particular tub being coupled to the next tub. So say the rate of outflow in one tub can be equal to the rate of inflow into the next tub. And we sort of capture this mathematically using these coupled systems of differential equations, which is really all that we need to then consider our SIR type models. But before we move on to SIR type models, I'll just ask if there's any questions about differential equations.
I have a question.
Sure, is that Andres?
Yeah. Can you hear me, right?
I can hear you, yeah.
Yeah, so do you think there are kind of like exercises in which we can practice this? Because with the letters, it looks very, theoretical, but if you put numbers on it, it's way easier to understand.
Yeah, so I don't know of any exercises off the top of my hands, although in the tutorial on Wednesday, you'll get a chance to play around with these differential equations using some simple Python code in which you can substitute particular variables for actually real numbers, and then the computer will do the hard work for you of actually tracking the changes in the rates of these. So I think the tutorials will allow you to get a little bit better sense of how these differential equations behave through time. In terms of a general resource for getting some familiarity with differential equations, if you haven't encountered them previously, there's a great book by Steve Alner and a second author that I can't remember his name right now, but it's just called Dynamic Models in Biology, and it's a great book for understanding the rationale for these simple differential equations. And in fact, the simple sort of tub model that I used as an example was from that book, and I think it's called Dynamic Models in Biology.
Okay, perfect. Thank you. Yeah, I will look for the book.
Cool. Are there any other questions? All right. Well, feel free to reach out to me if you have any questions after the lecture today about differential equations. I know we're going fast through the differential equation stuff, but really I just wanted to give you some intuition about what we're doing with the differential equations, because it's important to understand that for the SIR models. But really what any given differential equation is really trying to describe is the rate of change of a particular variable through time, which could be the amount of water in a tub. Or as we'll see in a second here, they can also be used to describe the rate of change in, say, the number of infected individuals in a population. So I think just thinking about these differential equations as just the rates of change per unit of time is the easiest way of thinking about these differential equations for this lecture. All right, so we've had some preliminary introduction, although I know that was not probably enough for complete comprehension into these differential equations. So now we can actually turn to SIR type models. And what SIR models are they're compartmental models that keep track of the infectious status of individual hosts using a system of differential equations. So the SIR part of SIR models stands for susceptible, infected, recovered. And these different compartments stand for different infection status of the different hosts. So a host can either be susceptible, infected, or recovered. And the infectious status of an individual host will be allowed to change through time. So what we generally assume is that everybody starts out as susceptible, but then the susceptible individuals can become infected by coming in contact with an already infected individual. That's what this dotted line here is supposed to represent in this flow diagram, that there's some feedback between already infected individuals and susceptible individuals, which causes susceptible individuals to become infected. And then once an individual becomes infected, they'll stay infected for a while, and then ultimately recover from that infection, in which case we'll assume they then move into a compartment that we'll call recovered, which means they're sort of immune to becoming infected again. So this basic flow diagram suggests that there's basically two different processes here that we need to think about and need to model. There's the transmission process of how infected individuals infect susceptible individuals. And then there's the recovery process of how infected individuals recover. So we'll start with the transmission process. And so transmission in these SIR type models is normally modeled assuming random mixing. I always think about this in terms of like simple models from chemistry, where we have just say a bunch of gases or molecules in a cylinder, and those random gas molecules are bumping into each other and reacting with one another. Here in this case, what we mean by random mixing is that we have a population of susceptible and infected hosts sort of in a given population that are randomly bumping into each other, and infected hosts are potentially infecting susceptible hosts. And so the overall rate at which new infections occur, which we'll call the incidence, depends on the rate at which susceptible hosts come into contact with infected hosts. And so the incidence equals S, the number of susceptibles, times the number of infecteds, times some transmission rate, beta. And what the transmission rate beta here reflects is the contact rate between susceptible and infected hosts. How often are two potential hosts that can infect each other coming into contact with one another. But we actually generally try and capture with beta two different processes at once. We try and capture the overall contact rate at which different individuals are coming into contact, and then the probability of an infectious contact occurring when that contact happens. So we can actually think about the transmission rate beta as being the rate at which potentially infectious contacts occur between susceptible and infected hosts in the population. And so what these models are assuming here is basically what we refer to in the physical sciences as a mass action. The rate at which new infections are occurring will be equal to sort of the density of susceptible and infected hosts. And so the higher the density of susceptible and infected hosts, the more these susceptible and infected hosts will be coming into contact with one another and infecting each other. But we assume that each host within each compartment, within the S or the I compartment, is interchangeable. So we don't really keep track of the individual identities of individual susceptible or infected hosts. We just keep track of the overall number of susceptible and infected hosts. And there's two different ways we can model the contact rates between different infected hosts. The standard way of doing it for most human infectious diseases is to assume that the instance or the rate at which hosts are contacting one another is frequency dependent. So instead of just having the contact rate be equal to the density of the susceptible host times the density of the infected host, we actually assume that the contact rate is proportional to the frequency of susceptible hosts. And this is just a way of accounting for the fact that in most human populations, the rate at which hosts contact one another doesn't necessarily scale proportionally to the density of the hosts in that population. So we can think about this for two given human populations. If we consider, say, New York City, which has a population size of about 8 million, versus Raleigh, which has a population size of about 500,000, and we assume that the overall sort of size between these cities is similar, that would mean that the population density of New York City is about 16 times larger than Raleigh. But we don't necessarily think that hosts in New York City are actually coming into contact with one another. 16 times higher than they are in Raleigh. We expect that the overall rate at which two hosts or two humans contact one another in these cities is probably less likely to be about the same. I mean, it might be slightly higher in New York City because people are riding around on subways. But the overall idea here is that in human populations, people have some control over who they come into contact with. And so the rates at which contacts occur are more likely to be frequency dependent than density dependent. We can contrast this with another system where rates of contact probably do actually depend entirely on the density of susceptible and infected hosts. And when I think about density dependence, I generally tend to think about animal populations. If we think about, say, cattle in a feeding pen, the cattle really don't have as much choice about who they come into contact with another. So if we increase the density of cattle in a feeding pen, the overall contact rate at which these animals are coming into contact with another is probably going to increase proportionally with the density of the cattle in that pen. So generally in infectious disease epidemiology, we model human infectious diseases using these frequency-dependent models, and animal and plant diseases using these density-dependent models. But really, you can see that the overall rate at which new infections occur under these two different parameterizations is very similar. One just accounts for the fact that the rate at which susceptible hosts might be coming into contact is frequency-dependent. Okay, so we talked about how we model transmission. Now we need to also talk about how we model recovery. And so the overall rate at which a given individual infected host recovers, we'll assume is equal to a constant recovery rate, gamma. So that means that the total number of recoveries in the host population at a particular time will be equal to gamma times the total number of people infected, or this is the rate of total recoveries in the population. So there's some things to note here is that means that if the recovery rate is gamma, that means that the average infectious period for a given infected host will be the 1 over gamma, or the reciprocal of gamma. So the mean infectious period will be 1 over gamma. Making this assumption that everybody stays accepted for the same amount of average time means that how long individuals stay infected for is going to be exponentially distributed, which may or may not be a good assumption for different infectious diseases. So we've seen exponential distributions already several times in this class. For example, when we talked about the rates of coalescence in a population, that coalescent rate or waiting time to a coalescent event also followed an exponential distribution. And what we know about exponential distributions is that they have a very long tail. So a given individual could potentially stay infected for a long period of time. But nevertheless, we generally tend to make this assumption that individuals stay infected for an exponentially distributed amount of time because it makes the model simple. And even if that's not completely realistic, it generally does a good enough job to capture the overall infectious disease dynamics in a given host population. So now we can return to our flow diagram where we were tracking the movement or flow of hosts between these different compartments in our SIR model, and we can reformulate this as a system of differential equations. And so what these three differential equations correspond to are the rate of changes per unit time of the number of susceptible, infected, and recovered individuals. So if we look at the differential equation for the number of susceptible hosts, ds dt, we can see that the rate at which the number of susceptible hosts is changing in our population is just equal to the instance beta si, or the negative instance, meaning that basically there's an outflow of susceptible individuals at rate BSI. We can contrast that with the rate at which the number of infected individuals is changing, and that's equal to the rate of incidence minus the rate at which infected individuals are recovering, gamma I. So if you recall back to our simple toy example of water flowing in and out of the tub, there the differential equation for the amount of water was simply the rate at which water flowed in minus the rate at which water flowed out. And now for our differential equation for the number of infected individuals in the population, we can see that something very similar is happening here. It's really the rate at which infected individuals are flowing into the I compartment, which is beta SI, minus the rate at which infected individuals are recovering or flowing out of the infected compartment, which is gamma I. And so even though these differential equations are a little bit more complicated than what we considered before with our simple water in a bathtub model, we can see that it's really, in some sense, it's very similar in that our differential equations, or the rates at which our variables are changing, are still equal just to the rate of inflow minus the rate of outflow in these different compartments. Okay, so now we can look at what the epidemic dynamics look like under this simple basic SIR model. And early on in epidemic, what we'll see happen is that the number of infected hosts under an SIR model will grow pretty much exponentially. So we'll start out with just, say, a single infected host, and the number of infected hosts will grow over time. And at first, that rate of growth will be very slow, since there'll be few infected hosts in the population. So the incidence, that beta SI term, will be very low. But as the number of infected individuals starts to grow, that incidence term beta SI will also grow. And as long as S, or the number of susceptible individuals, is still also fairly large, which is shown here in this blue curve, the overall incidence will also increase very rapidly. And so during the early stages of an epidemic, we can actually approximate the rate of growth of the number of infected individuals pretty accurately, just assuming an exponential growth model where the rate of growth will be equal to the transmission rate minus the recovery rate. But over time, what happens is that eventually there'll be a depletion of susceptible hosts, right? The fraction of susceptible hosts shown in this blue line begins to plummet. And eventually we reach an inflection point where instead of incidence growing over time, the rate of new infections actually begins to decline over time, and we go over the hump of this epidemic. And so what eventually happens is the epidemic starts to burn itself out because the epidemic exhausts its supply of susceptible hosts. There's no longer enough new susceptible hosts to become infected. And so the incidence of new infections starts to decline, and eventually the overall prevalence will decline to 0 as well. Okay, so we can do a couple of interesting things using this simple basic SIR type model. The first thing that we can do is we can look at the basic reproductive ratio. And so we've talked about the basic reproductive ratio, or R naught, several times in this class already, because we've already looked at some phylogenetic methods for estimating R naught from pathogen sequence data. But I think it's worth revisiting R naught now that we can think about R naught in terms of an actual epidemiological model. So the basic reproductive ratio, again, just to remind you, is the average number of secondary infections caused from a single infected individual in an entirely susceptible population. And so R naught under our simple SIR model is equal to the transmission rate, beta over gamma. But the way that I like to think about this, because it makes more sense to me intuitively, is to think about R naught as the transmission rate, beta, times the average infectious period, which again will just be 1 over gamma, or 1 over the recovery rate. So we can think about this as the rate at which new infections are caused by a single infected individual times the duration or length of time that that individual remains infected. And so what you can show is that for an epidemic to take off and for prevalence to actually increase in a population over time, R0 must be greater than 1. And so we can just look at this visually by simulating epidemic dynamics under our simple basic SIR model by varying R0. So what I did here was I kept the recovery rate the same, but I increased beta, so R0 became larger and larger. And what you see is that for R0 equal to 1, which is shown in the blue line here, the epidemic never takes off. We just remain at a single infected individual through time. For an R0 of 2, it takes a while, but the epidemic does eventually start to grow. Whereas if we increase R0 or the transmission rate even higher, the epidemic spreads more and more rapidly. And so it's probably a timely or time-relevant thing to bring up is that, you know, the reason we're all bunkered down at home watching this lecture on Zoom rather than in class is that what we're trying to do right now with the COVID-19 epidemic is, you know, trying to get this epidemic curve to look as much as possible like the orange line here, or even below the orange line, more towards the blue line, to get R0 as close to 1, so the epidemic stops spreading and we don't overwhelm the healthcare system by having a large number of new infections every day. So one important thing to note is that R0 is not simply a measure of the infectiousness of a given pathogen. It also depends on the rate at which contacts occur in a given host population. So a given pathogen, in theory, could be highly infectious, but have a low R0 if it was spreading through a population where the contact rate was also very low. But generally, the transmission rate is going to be correlated with the infectiousness of the pathogen. In terms of the more infectious a pathogen is, the easier it is going to be transmit. So the greater proportion of contacts between hosts that are going to become potentially infectious contacts. But we can see overall that in this cool infographic that the R0 of different pathogens varies greatly by, you know, a couple of orders of magnitude at least. We have everything from pathogens with very low R0 values, like rabies and syphilis, to things with very high R0 values like mumps and measles. And fortunately for us, what generally tends to happen is that there's some negative correlation between the deadliness or severity of a given pathogen in terms of how virulent or pathogenic it is and its R0. So pathogens that tend to be highly virulent or deadly, say like rabies or Ebola, tend to have lower R0s than things that are highly infectious, like measles or mumps. Okay, so that was the basic SIR model. Sorry about that. And that's interesting because we can do stuff like calculate R0 under that basic SIR model. But ultimately, not much interesting or exciting can happen under that basic model. Either R0 is below 1, and so the epidemic just sort of fizzles out over time, or R0 is above 1, in which case the epidemic will take off, but as the epidemic depletes the number of susceptibles in the population, the epidemic will eventually burn out and crash. So in order to actually get more interesting epidemic dynamics, what we have to be able to do is replenish the supply of susceptible individuals in our population And the way that we do that is through adding host demography into our basic SIR type model. So the supply of susceptible hosts can be replenished by new individuals being born into the host populations. And so generally what we assume under these models is that hosts are born into a population at a constant rate, which we'll call nu. And then deaths occur at a constant rate, which we'll call mu. And so that means that the average lifetime of an infected individual will be equal to 1 over mu. So if the death rate is equal to, say, like 1 over 70 years, then the lifespan of an individual will be 70 years. It's common to assume that the birth rate is equal to the death rate in the host population, just so we're at demographic equilibrium. In other words, so that the total host population size doesn't change through time. But although this is a common assumption, you really have to be careful about making this assumption because for many host populations, this is not true. In many populations, the population size is either growing because the birth rate is higher than the death rate, or declining because the death rate is higher than the birth rate. But for our case, we'll just consider cases today where we're at demographic equilibrium and the host birth rate is equal to the death rate. So we can very easily modify our basic system of differential equations by adding births and deaths into our model. What's important to note here is that when a birth event happens, newly born individuals always enter the susceptible population. So births only show up in one equation in our system of differential equations. All births are assumed to enter the susceptible population. And so the births only show up in the differential equation for the number of susceptibles. Meanwhile, we assume that an individual with any infectious status, susceptible, infected, or recovered, can die, so we have a death term in all 3 of our differential equations, accounting for the rate at which susceptible, infected, or recovered individuals die per unit time. And so then we can consider what R0 is under this model with host demography. It's very similar, but we have to take into account the death rate. So the overall R0 is the transmission rate, beta, over gamma plus the death rate, mu. So that mu takes into account that the average duration of an infectious individual can be modified by the potential death of that host, which generally isn't that important for acute infectious diseases where infections occur on a very rapid timescale and hosts don't stay infected for that long. But if we can start to consider chronic diseases, say like HIV or hepatitis C, where hosts remain infected for a long period of time, it is important to take into account that death rates in the R0 expression, because that death rate can determine how long an individual host stays infected for. What's really interesting about these SIR type models with host demography is that because susceptible hosts get replenished through births, what we can wind up with are extremely sort of interesting, complex population dynamics, where the overall number of infected individuals in the population can fluctuate widely with these large oscillations through time. In dynamical systems, these types of dynamic behavior is called damped oscillations. So we get big oscillations in the number of infected individuals through time. But eventually, if we run out these dynamics for long enough, the overall number of infected individuals will tend towards an equilibrium. And we can compute what that equilibrium is. If this was a course on sort of mathematical epidemiology, we could spend days or weeks talking about the equilibrium values for these different types of models and whether they're stable equilibrium or not. I'll just mention that for this SIR model with demography, the interesting thing is that the larger R0 is the smaller the equilibrium value of the number of susceptible hosts. is in the population. And so that means that the higher R naught is, the more the susceptible population will be depleted after a large epidemic. And so the harder it will be for another infectious disease or the same infectious disease to sort of reemerge in that population, unless births have replenished the supply of susceptible hosts in that population. And what we know about sort of these oscillatory dynamics for many infectious diseases is that the period of these oscillations, how long we have to wait between major peaks in these epidemic dynamics, is very sensitive to the host birth rate. And so the classic example of this was in the US and the UK after World War II. The periodicity of common childhood diseases like measles and mumps changed right after World War II because the birth rate went up in the host population. So before World War II, measles and mumps had sort of periods of 2 to 3 year waiting periods between large epidemics because there had to be a replenishment of susceptible hosts. But what happened during the baby boom after World War II is that the birth rate became high enough that basically there was enough susceptible hosts in the population for there to be a large epidemic in the host population every year. And so you got these seasonal outbreaks of common childhood diseases like measles. What's interesting is that you can still see sort of the effect of different birth rates on the period of these oscillations in different modern day human populations. So if we look at, say, the dynamics of measles in sub-Saharan Africa, in countries like Niger, we can actually still see that we see a mix of different types of epidemic dynamics, where we get some populations that have large epidemics or large peaks, seasonal peaks in prevalence every year, like in Zinder here. Whereas in other populations, we have to wait many years for there to be a buildup of susceptibles in the population before we can get another large outbreak. And so what's interesting about this is that we can look at the periodicity of these diseases in terms of the host birth rate. And the periodicity of these diseases will depend in part on how seasonal these diseases are. If seasonality is very strong, for example, if human movement patterns is very seasonal, then you can just have seasonal dynamics caused or annual epidemics caused just by very strong seasonality. But if you look for a given strength of seasonality, what you can see is that as the birth rate becomes larger and larger, what we tend towards is having big annual peaks in prevalence every year. Whereas if the birth rate's lower, say below 20 per thousand, even at relatively low rates of seasonality or relatively low seasonal forcing, we often get multi-year periodicity, meaning we have to wait multiple years for enough susceptible individuals to build up in the population to have a big epidemic again. Sorry, I just wanted to check out in time. Lastly, the really interesting thing that we can do with these SIR type models is we can look at what fraction of the host population we have to vaccinate or remove through such measures as quarantining to be able to eliminate an infectious disease from a host population. So we can consider this by looking at a modified version of the SIR model, where a certain proportion, which we'll call P, of newly born hosts get vaccinated at birth. So if we look at this modified system of differential equations, what we see is that in the susceptible compartment, new hosts are born at rate mu, but only a fraction of host 1 minus P actually get born into that susceptible compartment, the rest of the hosts, the fraction P, immediately get moved into what we think of as the recovered compartment, meaning they're already sort of immune to the pathogen, so they can never become infected. So we can effectively treat them as if they were already exposed to disease and recovered. And what's interesting about this model is that dynamically, this model is very similar to a model where the basic reproductive number, or R naught, has been reduced by a fraction 1 minus P. And this is because what the R naught is, or tells us, is the average number of new infections per infected individual. And so if we're vaccinating a fraction of the population P of the host population, then the remaining fraction of 1 minus P hosts aren't going to be able to become infected. So R naught gets reduced by a factor 1 minus P when we vaccinate a fraction P of the population. And so what's interesting under this model is that we can then look at what fraction of the total population we need to vaccinate in order to eliminate the disease from the population. And so in order to be able to eliminate the disease from the population, we have to drive R naught below 1. So we need to find the critical vaccination threshold, or this value of P, of the proportion of the population that we need to vaccinate to drive this R naught below 1. And that turns out to be this critical proportion, PC, equal to 1 minus 1 over R naught. And so this is one of the most famous sort of equations in a lot of mathematical epidemiology, because through this very simple back of the envelope calculation, given the R naught of a particular pathogen, you can very quickly figure out what proportion of the population you need to vaccinate in order to eliminate the disease from the population. And what's interesting is that the proportion that you need to vaccinate grows non-linearly with R. So as R naught increases, you have to vaccinate more and more of the host population. So for something very, very infectious, like measles, we would basically, which has a very large R naught, usually cited around, being somewhere around, say, an R naught of 16, we would have to vaccinate basically everybody in the population to eliminate measles from the population. Meanwhile, for a disease like influenza or COVID-19, one of these sort of common respiratory pathogens, their R naught is much lower. It's normally somewhere between like 1.5 and 3. So in that case, we would only have to vaccinate, say, about 2/3 of the host population in order to eliminate that pathogen from the population. So I've seen, actually just over this weekend, I saw sort of several disease modelers or epidemiologists, talking to reporters about this and saying, or quoting this figure of, well, if we were just able to vaccinate, say, 65 or 70% of the population, or if 65 or 70% of the population became naturally infected, that this disease would be eliminated from the population. But they, of course, never say actually how they come up with this figure. But I bet, if anything, they're just using this back of the envelope calculation of finding this critical vaccination threshold, PC, to find out how much of the population you need to vaccinate. Okay, I can see, because of the time, I need to sort of speed up a little bit. So we get through all this. I'm just going to quickly note that there's many different common variants of these common SIR models. There's SI models where we completely ignore the R compartment because we assume hosts never recover. These were commonly used to model things, say, like HIV before the era of antiretroviral drugs, because hosts can never become could never recover from infection. There's also models like the SIS model, where instead of hosts recovering into a recovered compartment where hosts have immunity, um, infected hosts just recover immediately back into the susceptible population. So they can be immediately infected again. And these models are often used to model infectious diseases with no protective immunity, which is common for some bacterial STDs like gonorrhea and chlamydia. So there's several common variants of these. What I also wanted to talk about today, though, there's sort of a more complex extension of these SIR models that either consider the possibility of there being multiple different pathogens circulating in the same population. We'll skip these today because they get actually quite complex because these different pathogens interact with one another through immunity in the host population. So instead of just keeping track of the number of susceptible individuals in the population, we have to keep track of the numbers of susceptible individuals for every single pathogen type. And instead, what I want to talk about briefly today are what are known as multi-host systems that can be used to model host heterogeneity, meaning that we actually have different types of hosts in our host populations. And these models are very useful because we can account for all different forms of host population structure using these models. So if we allow for there to be different host types or host classes, we can account for things like age structure in the host population, or gender structure if there's males and females, risk structure if there's high risk and low risk individuals in the population, and also very importantly for especially diseases of plants and animals that aren't as mobile as human populations, we can account for things like spatial structure. And the basic way that all of these multi-host models work is that instead of just having a single compartment for the SI and the R class, what we wind up with is assigning each host both an infectious status in terms of S, I, and R, and also assigning each host to a class. So if we had, for example, a two-class SIR model where we divided the host population into states 1 and 2, we would have to keep track of the number of susceptible hosts in both host population 1 and 2, as well as the number of infected hosts in populations 1 and 2. But what we generally assume under these models is that pathogens can be transmitted back and forth between different classes. So now when we want to model transmission between different classes, we have to consider basically all the different ways that a pathogen can move between two different host classes. And so we model this using a general transmission matrix, where each element in this matrix gives the transmission rate between two different host populations. So beta 1,1 here would be the transmission rate between hosts in population 1, whereas beta 1,2 would be the transmission rate of from hosts in population 1 to hosts in population 2. Very similar to the types of transition matrices we saw earlier in the class when we were considering about like migration or movement of individuals between different populations. Okay, so now we can actually consider our flow diagram and then the differential equations for a model with two different classes. Again, the key feature of these models is that we have to take into account not only that individuals can move between these different compartments in terms of their infectious status, SI and R, but also that infected individuals in each class can potentially infect host in the other compartments. So basically, we always have to keep track of the fact that a susceptible host in each class can be infected by an individual in a different class. And so what this means practically in terms of our differential equation models is that for we'll just consider the differential equations for the number of infected hosts, is that there's 2 incidence terms now in our model, because we have to keep track of the incidence, or the number of new infections arising from transmission within that population, but also infections arising from transmission between these different populations as well. I will skip that in the interest of time. What's one really common application of these models is to model risk structure in a population when we have individuals at high risk and low risk. So commonly, we think about these types of models for considering risk structure for, say, sexually transmitted diseases, where there's a high risk group and a low risk group. Say the high risk group are people who rapidly come into contact with other sort of risk-taking individuals. And then there's low-risk individuals who sort of avoid such risky contact behavior. And this is sort of just one particular instance of what's known in infectious disease epidemiology as the 80-20 rule, which states generally that for any given infectious disease, the majority of new infections are going to arise from a small fraction of the host population. And generally, it's cited as it being sort of 80% of new infections arise from only 20% of the population, but the exact fractions aren't what is actually important here. What's actually important here is just that the majority of new infections are going to arise from a small subset of the population. So we can consider a basic SIS type model that takes into account high and low risk groups. Here we're using an SIS model instead of an SIR model, because we're thinking about sort of a sexually transmitted disease that doesn't have any long-term immunity. So infected individuals recover back into the susceptible compartment. And so we can see, if we look at the differential equations for the infected individuals in the high and the low in infected compartments, again, we're keeping track of new infections arising from both infections within that individual risk group as well as infections between the different risk groups. And so what we'll do to sort of consider the case of something like the 2080 rule is we'll consider that the majority of the population is actually in the low risk group. So 800 individuals are in the low risk group, and only 20% or 200 individuals are in the high risk group. And we'll parameterize this in terms of a transmission matrix where the rate of transmission is very high in the high risk group and low otherwise. So low in the low risk group and low between the high and the low risk group. So most of the transmission here is really occurring amongst individuals in the high risk group. And so using this model, we can look at the infectious disease dynamics through time. And what we see, not surprisingly, is that everybody in the high risk group very rapidly becomes infected. Basically almost everybody in the high risk group becomes almost immediately infected, whereas individuals in the low risk group take longer to become infected, and the total fraction of infected individuals in the low risk group never becomes as high as in the high risk group. So I'm just going to check on time real quick again. I think we have enough time to make it through to the end. And so what's interesting about these risk structure models is that we can, again, consider how much of the population we need to vaccinate in order to control the infectious disease. What fraction of individuals do we need to vaccinate in order to suppress the infection so that R naught goes below 1. That's my cat, if you can see. So our overall goal now is to, again, get R naught below 1, but the question becomes much more interesting because we can now ask, well, what proportion of the high and the low risk population do we need to vaccinate in order for R naught to go below 1? So computing R naught becomes a little bit more complex in this type of situation, because now we have multiple different risk groups or different host subpopulations. But what we can do is we can think about this in terms of what's known as a next generation matrix, where each element in this matrix will represent basically the R naught for the number of new infections arising in each population due to infections from another population. So for example, the upper left element of this matrix gives basically the number of new infections that would arise in the high risk group from the high risk group, whereas the upper right element would correspond to the number of new infections in the high risk group from the low risk group. And we can weight these individual sort of R naught values, or the elements of this matrix, by the proportion of the population that falls in each risk group. And what we can do if we want to compute the overall R naught, sorry, forgot one thing. Since in this case, we're also considering the effect of targeted vaccination, we can also consider the effect of vaccinating a certain proportion of the different risk groups. So 1 minus pH here would be the fraction of the high risk group that we left unvaccinated. And so under this type of model, what we can then do is calculate the overall R naught, which just on a technical note means that what we have to do is take the leading eigenvalue of this next generation matrix. I don't want to get lost in the weeds here about what taking the leading eigenvalue actually means, but just intuitively we can think about sort of taking this eigenvalue as a way of averaging over sort of the different initial conditions that we could start with if we started the pathogen in these different risk groups. So we're not weighting our R naught just by starting the pathogen in one particular host population. We can sort of weight the contribution of each host risk group to the next generation in terms of their relative representation in the overall population. So what we can do then is, under this risk structured model, we can look at what fraction of the low risk and the high risk individuals do we actually have to vaccinate in order to get R naught below 1. And so an R naught value of 1 is shown here by this sort of pinkish purplish line here in this contour plot, meaning that above this line, the R naught will be below 1, and below this line, R naught will be above the line. So where we want to be is sort of above this 1 line. And what's interesting here is that we can see that we could potentially vaccinate a very large fraction of the low risk population, but still have an R naught above 1. Whereas if we fractionate even 50 or 60% of the high risk population, we're almost guaranteed to have an R naught below 1. So obviously what we want to do here is then target our vaccination strategy towards the higher risk group, so we can just vaccinate a smaller fraction of the total population. And we can actually look at what fraction of the population we would need to vaccinate under these different combinations of vaccinating the high and the low risk groups. And you can see that here, if we look at the corresponding R naught in the plot on the left, we can get an R naught value below 1 by vaccinating, say, 25% of the low risk group and say 55% of the high risk group. And this would correspond to only needing to vaccinate, say, 40% of the total vaccination. So by looking at these risk structure models, what we can see then is we can tailor more targeted intervention strategies towards targeting high-risk individuals, and we can actually much more easily control these infectious diseases by targeting our response towards these high-risk groups. So some final thoughts about these models. What I hope I showed you today is that by looking at these overall relatively simple SIR type models, we can answer a bunch of different questions and improve our understanding about the epidemic dynamics of different pathogens. So we can see, why different epidemics grow rapidly and then decline. We can look at why some outbreaks take off and why others do not, in terms of the R naught of these different pathogens. We can see why some diseases remain endemic in a population, whereas others only have periodic outbreaks or have epidemic dynamics, by looking at SIR models that consider host birth rates and therefore the effect of host demography. And we can see why some pathogens go extinct and what we need to be able to do in order to eliminate others in terms of the fraction of the population that we need to vaccinate in order to achieve an R naught below 1. So some final thoughts is that the beauty of these SIR type models is that they allow us to very easily model the natural history of a whole bunch of different infectious diseases and their epidemic dynamics, and that we can easily take into account almost any form of host population structure just by adding additional compartments to these SIR type models. And this is especially useful once we start considering these multi-host models that can be used to, say, consider different host populations, because we can very easily add a large number of potential different subpopulations to our model without increasing the overall complexity of our model too much. And this is especially useful for modeling the spatial dynamics of these diseases as well, even though we didn't really talk much about spatial dynamics today, in terms of we can model the spatial dynamics of these diseases using what are known as metapopulation models that basically are a form of a host structured model where we allow different host populations to live in different areas, which are very useful for modeling infectious diseases, especially in agricultural systems of like animals and plants, where we know the mobility of the host isn't as high as in human populations. And so incorporating spatial structure is very important. The grand challenge, which we'll talk about more next week, is that when we consider these increasingly complex models with more and more compartments for different disease states or for different subpopulations, as that it becomes very challenging to parameterize these models in terms of if we don't have very detailed data about the number of infected individuals in each population or the sources of new infections into the population. It becomes very hard to sort of estimate where new infections are coming from, and in terms of being able to parameterize the transmission rates between these different populations. We generally don't know what these transmission rates are unless we're able to actually estimate these things from empirical data. So what we're ultimately building up towards is to be able to use these types of epidemiological models, which really help our understanding of, in terms of the epidemic dynamics, but be able to actually fit them to pathogen genetic data, which, as we've seen already in this class, can provide a lot of information about where new infections are coming from and the sources of transmission. So over the next 2 weeks, our ultimate goal will be to take these types of epidemiological models and bring back in the molecular epidemiology in terms of